So we have learned about the matching in graph, and we proved the formulas to compute the size of the largest match in graph. Okay, then what's next question? Next natural question is how can we find largest matching in graph? So this is natural question. How can we find the maximum matching? Of course, there are obvious way. One obvious way is to check all possibilities. There are m edges, say there are m edges. Then one can check all possible 2 to the m subsets of edges. However, this is not effective because, usually this 2 to the m is an exponential function. And usually we consider exponential function is quite large. And but algorithm which requires that many checking, we don't consider them effective. Natural question is, can you find a better algorithm? Say some polynomials here instead of exponential function. Okay, so maybe, if we just want to find the large matching, not necessarily maximum, then what we can do is we greedily add edges. So we take one edge and then take another edge, which is distinct from the previous edge, and take another one, and then you do it until you cannot do anymore. Then you get a matching. If here's a maximal matching, meaning that this matching is included maximal, but that means, this matching means that there are no other matching which properly contain this M. But this is not necessarily the largest matching we should for. For example, consider this 6 vertex path P6. Then what we can do is we can take these two edges. Then that's a maximal matching. There are no other matching which contains both of these two edges. However, there are bigger matching. So this is maximum matching. In this case, this is actually the only maximum matching. It's not a maximum matching. Maximum matching. This is the maximum matching, but this is a maximal match. So we want to distinguish between maximal and maximum. In this course, when we say maximum, it means that the one with the largest size. Maximal means that it's included maximum, meaning that there are no other things which properly contain it. Okay, so this is giving a maximal matching, but not maximum matching that we wanted to find. Then what can we do? Okay, so in order to find the better algorithm, we need to find some other concepts which will allow us to find the better algorithm. So, natural question is what other concepts? Maybe, other concepts which are more tractable, concepts, which, say, test for maximum matching. They characterize, let's say. If we have some characterization of maximum matching, then instead of checking whether a matching is maximum matching, we just check the alternative characterization. Then if that characterization is happen to be more tractable one, more easy to deal with, or more concrete, then it might give us a better way to find the maximum match. Then, how do we find such a concept? So what we want to do is that we want the characterization of maximum matching, meaning that when there is a matching, we want to check whether, we want to know whether this is maximum matching or not. That means for a given matching M, we want to check the resistance of big or larger matching, the M. If there are no other larger matching, then this is a maximum matching. If there is a larger matching, this is not maximum matching. So, for example, if we have say matching M and another matching, which is a larger matching, blue one has 1, 2, 3, 4, 5, 6 edges. Black one has only 5. If there are larger blue matching, then what do you see here? We have drawn the original matching M, and then we have drawn a larger matching M prime. And then what we see here is that there are certain edges, and certain edges of M and M prime are concatenated to certain paths. And some of them are exactly coincide, some of them are not. And then they are alternating here. And you see that this component has one black edge, one blue edge, one black edge, one blue edge. And this path has 2 blue edge, 2 black edge. This is 2 blue edge, 1 black edge. Somehow, here we have 1 more blue edge. So this kind of give us some intuition that we might want to give name of this kind of path. And this path having 1 more edge is kind of essential reason why M prime is bigger than. Or, finding such a path is a way to check or verify that M prime is indeed larger matching than M. So, this motivates the following definition of alternating path and programmatic path. Let's say that we are given a matching M. And we give a name for such a path that M alternating path is the path that alternates between the edges of N edges not in M. Then we say that on M augment help. Maybe right. Let's write it this way. M alternating path whose endpoints are not covered by M is called on M augment. For example, here, this is an M alternating path. This is an M alternating path because it alternates between adjective M and adjective not M. And what? An M alternating path whose endpoints are mixed by M is an M augmented path, and this is M augmented path. However, this is not an M augmented path because end vertex is covered by M. And this is also not M augmented path because end vertex is covered by M. But here, these vertices are not covered by M, so this is an M augmented path. With this definition, one can easily check that the existence of M augmenting path implies that the M is not the maximum matching. Okay, maybe I would say it is easy to check. Okay. We want to say that these two are equivalent. So M is not a maximum matching, then there is an M augmenting path, and vice versa. If M is maximum matching, then there are no M augmenting. We want to show this. The WTS here it means want to show. Okay, so maybe let's define this terminology, this notation to make our discussion easier. Let's say symmetric difference G delta H is a graph with a H set E of G, symmetric difference with E of H, and they no no isolated bodies. Here, if you take the symmetric difference of these two, and this disappear, then these are still there. So here, the symmetric difference of M and M prime are disjoint union of the two pathways. Then we can prove the theorem by errors that the matching M graph G is a maximal matching in G if and only if G has no M augmenting paths. And we can prove this. This direction is, kind of easy. How? If C is a M augmenting path. Then what we do is we replace the edges in G, edges in M, which also belong to P, with edges in P, which does not belong to M. Meaning that this was originally M, and you have this M augmenting path. Then you delete this and you add these two. Then you have a 6 edge matching, which is larger than the before, the matching M. So this direction is easy. And we take the other direction. So assume that for this direction, what do we do? We take the contrapositive, then the existence of larger matching implies M augmenting. So that's what we want to show, right? That's contrapositive of this direction. Then consider that when G has a matching M prime larger than M, and that F is the symmetric difference of these two. And what do we have? Since M and M prime are both matching, and every vertex has at most one incident edge in M, and at most one incident edge in M prime. So every vertex is incident with at most one edge from its matching. Hence, the maximum degree of F is at most 2. Okay. Then how does this F look like? Some vertices might be isolated vertices, but okay, in this symmetric difference, we delete that, so it doesn't exist. So if there are vertex with degree 1, then the other one is either a vertex of degree 1 or 2. If this is 2, then it has another neighbor. If this is 2, another neighbor, and then at some point it's tau. So it's a path. Or theoretically, it could be also possible that there are like cycles of degree 1, 2. So essentially, maximum degree most 2. It means that the F is the joint union of paths and cycles. The components of F are paths and cycles. Then we know more. Each component is a path or cycle that alternates between edges in M and edges in M prime. So each cycle in F has even length, because it alternates between 2 and then it wraps around to come back where it starts. That's only possible when it has even length. But what do you know? Our assumption is that M prime has more edges than M. That means there exists some component which has more edges in M prime than then what? Such a component cannot be a cycle because, cycles have even length that contain exactly the same number of edges in M and M prime. That must be a path. And moreover, that starts and ends with edges in M prime because it contains more edges in M prime than M. As it is on M augmenting path. Okay, now we have the characterization using this concept of M augmenting path, which is a characterization for maximum matching. And using that, we can actually come up with an algorithm, polynomial time algorithm, to find the maximum matching. How do we do it? Essentially, instead of finding maximum matching directly, we want to grow a matching to maximum matching. We want to find the matching and then we replace with a larger matching until we cannot. And then this replacement, we use this technique for finding one M augmenting path, and then you replace edges, this edge to this edge to get a bigger one and bigger one and bigger one. While doing that, our main task is find the M augmenting path, or prove that there are no M augmenting paths, hence returning the current matching M. But the augmenting path is what we want to find, and the path is essentially you can grow one by one. So we do this augmenting path algorithm. And for our simplicity, we consider the bipartite. For non-bipartite graph, the algorithm becomes more complicated. So let's just assume this. And assume we have a bipartite graph. A with bipartition X, Y, and we have a matching M, and that the U or vertices in M not covered by M. So let's say you have a Y, X, and M. And what does this algorithm do? This algorithm, we want to find an M augmenting path for given matching M. Or if there are no such M augmenting path, then the algorithm we want it to return the fact that it doesn't have an M augmenting. So what do? We initialize S to be U and T to be empty. It is a quality which, we will update every time. And then essentially what we want to do is we want to, keep track of all possible M alternating paths starts from U. Here, I mean, if there are M augmenting paths, then the endpoints, both endpoints have to be missed by M. So it has to start from U and then ends here. So we want to find the M alternating path from here, then somehow ending here. Then what we want to do is we check all M alternating paths that starts from here. And then how do we check? We start from here and then we keep track of all possibilities. And then at each point, these are the vertices which is reached by the paths that we have considered so far. This is the subset of X which are reaching, and this is subset of Y which are reaching at the moment. So that's the role of this set. And what's our iteration? If our S has no unmarked vertices, then we say that M, we return that as M is a maximum matching, and we return this set as a minimum. Here, I mean, this is for bipartite graph. Then last time we proved the Koenig Elderberg, not last time, the time before that, we proved the Koenig Elderberg theorem, which says that the size of maximum matching is same with the size of the minimum vertex cover. And here, this is a proof that this is the maximum match. If you have a matching M, and there is a vertex cover of the same size, then that proves that the M is the largest matching. So, in this case, we found our maximum matching M. Otherwise, what do? We select an unmarked vertices. So initially, no vertices are unmarked, and then every time we explore all possibilities at that vertex, and we mark them, so that we don't have to come back again. So we select an unmarked vertex. Say X in F, and consider Y consider Y, which is the neighbor of X. Let's say we consider all of them. Consider each Y such that XY is not in M. So this is our X. Then we consider all Y, which is neighbor of X, through the edges not in M. Okay, and if Y is not covered by M, then trace back from Y to find the overwriting path. Meaning that you do this, and then somehow, okay, let's say your X was here, and your Y is here. Then from Y, you go back, and then take to U to obtain a augmented path. So remember, this is in S means that from here, somehow you take the M augmented path, M alternating path, and then reach it this at this F. And then from here, your next edge is towards the vertices which are not covered by M. And this M alternating path together with the last one give you an M augmented. Otherwise, this Y is passive to some, say, W in X by M. So meaning that this is your W. In this case, we say include this Y to T and W to S. And after exploring all such edges incident to X, we mark X and Y. So here, what you take this edge and take this edge and you add. Now what? These are all your vertices in S. And then you mark this. And then you take one unmarked vertex, say here. Then from here, you consider all edges exactly this. And those edges not in M. And then again, this is added to S. And then you mark it. And then you keep do that with your choice of next unmarked vertices out of this S. Then say from here, you have edges towards the outside. And you have this M augmenting path. You return it. And that's the end of the algorithm. And then you keep do that. So that's the case we get an augmented path. Otherwise, it's you keep add. But this is the situation, what happens here and here and here. We want to actually prove that this algorithm works. So if we're repeating this augmenting has algorithm or bipartite graph, here's a fractional matching. Then how do we find such matching? How do we verify that it is a maximum matching? Because it gives a matching and a vertex cover of equal size. So assume at the termination, one of the clear things is that this algorithm terminates every time you plot an edge, then you mark the vertices, and then same edge is never explored again. So at some point, every vertex is marked, and this has to happen. Assume at the termination, we have the sets X, Y, S T and no M augmented. Of course, if we find an M augmented path, we just take the intersection with we delete the intersection with the M augmented path, and then we add the edges in the augmented path not belonging to M, and we get a bigger matching. So that's not at the termination. At the termination, we must have a situation that no M augmented path was returned. Hence, it terminates by writing all vertices in S. Then we will show that its T union with X minus S is a vertex property or the same with M. So what do we have? We have, let's say, X. This is 0. Then what do you know? Every M alternating path from this U goes with start with the edge not in M, and then come with the edge in M, and then goes with the edge not in M, and come with that. So it enters X only on the edges of M. So at every M alternating path from U enters X only on edge of M. We know that every vertex of S minus U, the vertex in here, is matched by M to a vertex in T. So these vertices are in T, right? Once we have a vertex in T, that means that's vertex T, then its counterpart is added to S. So all the added vertices in S, which are not in U, are actually matched with the vertex in T. And what do we know? No edges of M joins S to Y minus T. So from here to, let's say this is T. From here, no edges of M are connecting these with the others. Because if these are, if there are, so this is already matched. With this vertices in T and vertices in S minus U are already matched, and these are not matched. That means this part is not matched with any vertices in S. And M alternating path, which is a vertex in S, then it can continue along any edge not in M. Whenever you have a M alternating path reaching some vertex here, and whenever there is some other edge which are not in M, you can keep going in this algorithm. And it has vertex to T. But what do you know? Since the algorithm terminates with marking all the vertices in S. So it's outside M, so in S and Y minus T. So these are all marked, right? And if there are edges between this and Y minus T, then in this algorithm, we can continue from here by adding this edge, and then add this to T. So we could have done more. That's contradiction to the fact assumption that we have terminated. So that means if we have terminated from here to here, there are no edges. So what do we know? No edges outside of M. And also we have already verified that there are no edges of M between X and Y minus T. That means in X and then Y, here we have T, Y minus T, we have S, and then X minus S. And there are no edges between S and Y minus T. Then what? Every edge meets one vertex here. So what? T union X minus S is a vertex. Okay, and then now what do we have to do? We just have to check that this has the same size as M. What do we know? As in this picture, these all vertices in T are matched with the, on edge in M. If, we find an M alternating path, then this is added to T, but that didn't happen. So we are at the termination without finding any M augmenting path. So since the algorithm find no M augmenting path, then we know that every vertex of T is covered by M. And each Y in T is matched to a vertex in S via on edge of M. And as U is in subset of S, each vertex of X minus S is also covered by M. Yeah. Then we have U S, and this part is covered by M, and this is T, and this part is also matched by T. The edges of M incident to x minus s, they cover no vertex of T. So these are matched by M, and then it's not matched to any vertex in T. And these are all only matched in here. So thus M has what? At least size of T plus size of x minus s at T. But these are all matched by M, and these are all matched by M, and those edges are all disjoint. But what do you know? Since there can be more larger matching than the size of vertex cover, we have that this M has exact size this, and that proves the theorem. So this shows that if we repeat this, if we apply this algorithm to find the M augmenting test, and using this you augment the matching to one larger matching, and then you repeat this until you get the maximum matching, then you actually get a maximum matching. And how many times do we have to do? And in each time you increase the size of matching by 1. So you might have to repeat this, the number of repetition is almost n over 2. You start from empty matching, and then you increase the size by 1 by 1, and the maximum possible size is n over 2. And each time, each iteration, what? We search from a vertex of x at, so what? Here, you take one vertex, and then you explore this edge, and you go, and then you keep doing it. But all the edges not in M are explored from bottom to top. This is only explored when we are considering this vertex, and no other time. And this edge is only considered when we are exploring from this vertex. So, no edge is considered twice. No edge is considered twice. So, M checking is sufficient. So, the number of edge checking is almost M. So, in total, how many times do you have to check for this algorithm? So, this algorithm's learning time is almost M times N. So, which is the polynomial time that we were seeking for. And there are actually better algorithms by Hopcroft and Karp in 1975. Better algorithm with a running time big O M times Q root of N. N is number of vertices, M is number of edges. And big O means that there are some constant, absolute constant, say 10 to the 10 times M Q root of N is sufficient. And we write this when we don't really care about this constant. And this was for bipartite graph. For non-bipartite graph, the situation is a bit different. So this algorithm is not really working, mainly because on edge could be, if there are, say, odd cycles, which is this M, this is M, then eventually one edge can be explored from both directions. Somehow you do this kind of, search for augmenting paths. And what? So this vertex, you go from here to here, and this edge is explored from this vertex point of view. Then again, this same edge, you can explore from here to here. So that makes the situation more difficult. So directly, we cannot really apply this algorithm, but there are algorithms known as Edmonds blossom algorithm. For non-bipartite, which has running time of 4 times equal of n squared. Essentially, what it does is that if you have this kind of odd cycle and some paths attached, we call it blossom. Then every time we have this kind of odd cycle, we contract it into one vertex, meaning that if your graph is something like this, you replace this with one vertex, and then you attach these edges to this one vertex. Then you replace your graph with a smaller graph. And then you repeat this until you have no cycle, which is a bipartite graph. There you apply this algorithm for finding M augmented paths. And then you come back to your original graph by uncontracting each vertex into its own cycle. That's roughly what you do. And there are also better algorithms known with this running time. Okay, we are not going to discuss about this blossom algorithm, as this is too complicated for our course. It's not too complicated, but we decide to skip it. You can look into it if you are interested in. Okay, we learned about this algorithm, and in the next video we will talk about stable matching. Sometimes we don't want to just find the maximum side matching. We might want to find some matching which are suitable for our purpose, and we will talk about it in the next video.